a kind of mesh network. In rail networks, we see less junctions and more kind of chain. In logistic networks, we have a directivity in the procedure. So it's a kind of ordered nodes. There is a lexicographic order. So some parts of the systems, they have to be first binded, then assembled together, and then the production, and finally the distribution. So there is a kind of directivity. Then there could be the power grids network, in which the main powerhouse is located at the, say, at the root, and then the leaf nodes, and they are distributed so as to distribute the power. So in any of this in this kind of types of real world graphs, you can see that one thing is very common. Whenever there is a increase in the number of nodes, then the average path length tends to decrease. Why? Because the nodes, they represent the people in the geographic area. So when more number of nodes are there, then what happens? This geographical barrier is getting dropped. So people are more connected to each other, and if whenever there is a spread of some information, some content, then it will quickly reach from one point to another point in the connected graph. So there is a steep fall of the average path length as the graph gets more connected with more number of nodes. So not only just the number of nodes, but also the connections increases. So now let's see that we have a fair idea of what the graph is. Now, what kind of different influence measures techniques are there through which we can find out the significance of a particular node? And then we will try to see that when we have identified the central nodes, then how we can spread the information in the network through those centrally identified nodes. Now, the significance of centrality. So centrality, as the word goes, central. So it's the significance, the important nodes in the network. So centrality is a connection-based measure, connection-based in the sense that it refers to the topology of the network. We must have a network with underlying connected structure from which we can derive centrality metrics from different perspectives. So we can, when we have recognized the central users, there could be different interpretations of it. So in a retail network, when we are identifying such central points, it means that we are identifying the important merchants that may act as a focal point in the merchandising. Then it could be the influential personality, or it can represent the influential events, the important events in online social networks, or online communities, blogs, etc. Then in a business-oriented network, they may act as the key strategies, or the spreaders of the news, or the purveyors of goods in a supply chain network. So centrality is basically influenced by the structure that is clear by now. And one more thing is how the information is being propagated. Is it propagating from one point to rest of the nodes, or from rest of the nodes it's coming to a particular node? Is it a one directional flow or bidirectional flow, or are there some kind of peak hours when the information is flowing? So that's why we see sometimes that some trends are very much active in social media, and then they tend to fall down. Maybe because they have been consumed well by the people. People have already gotten idea of, okay, this is the information that has been spread. So this trend of information spread can also be modeled using the centrality in the graphs. So now let's see the different types of centrality through which we can measure the importance of a node. So there are several types of centrality available. Some of them we are just taking up in this lecture. The first one is degree centrality. This is a measure that tells about that how a node is it's packed in its local neighborhood. So if a person is having a large number of friends, then it is said to be having a higher degree centrality. Similarly, there is one more centrality metric, that is closeness. Now, this is referring to the positioning of a node so that it can be reached from any part of the network in a convenient manner, in a less amount of time, or you can say less number of hops are required to reach to that node. Or if such a node is transmitting or is relaying some kind of information, then it can evenly spread to the network in less amount of time, as compared to the nodes that are located at the border of the network. So if we are sending information from a node that is located at the border or the circumference of the network, then it will take much longer time to reach to the other end of the network. Then there is decay centrality. This is centrality, just very interesting. It models that how information, when it is flowing, how it tends to deteriorate from the source of the information as we move towards the circumference, away from the source, basically. So how it deteriorates. Some error is getting into it, or some information is getting lost. So both ways the error can drop in. Then there is betweenness centrality. This is a measure of how well the node is positioned. So again, there is this positioning is coming, but now betweenness is a kind of relative positioning. Now we are also checking that how good this node is positioned, and such that it acts as a bridge or a gateway or a major connecting node between multiple communities. Okay, so such kind of nodes are very powerful nodes, as in absence of those nodes, the graph tends to get disconnected into multiple components. So such nodes are important to keep the entire network tied together. Then the information centrality. This is a centrality which is rather very closely connected to the entire graph. So in this case, what we do is we find out the centrality of the entire, the significance of entire graph, and then the node that is for which the centrality has to be computed, the information centrality, we take that node's connections out and then compute the information centrality again. And this relative thing, that is the whole graph and the whole graph minus that particular node, this is going to give you that how much drop in the information coverage is witnessed in absence of that particular node. So that is the importance, whose absence may lead to a drop in the information coverage. Then eigenvector centrality, this will give you the rank of the nodes in a connected community. So there are not only these centrality measures, there are large number of other centrality measures. But the thing is, we cannot say that a particular centrality is the best amongst all. So we often, for addressing the real world challenges, and sometimes we have some constraints also. So given all the challenges and constraints, the capacity of the network, we try to like assemble the some of these centrality and aggregate the final significance of the nodes. Now starting with the degree centrality, as we know that the degree centrality captures the connectedness of the local neighborhood. So in a graph like this, if we take up any of the nodes, say node 3, then we will see that to how many nodes it is connected directly. So in this case, node 3 is directly connected to 4 nodes. So this is 4 over here divided by the total number of nodes. So if we are just talking about the centrality, the degree centrality, so the degree centrality of the node 3 will be equal to 4. of the node 15 will be equal to 6. But we need a normalized version a node is always n minus 1 if there are n number of nodes in the star topology. So in that case, what happens? So that particular node would be connected to n minus 1, and the normalized version is also getting divided by n minus 1. So in the best case, degree centrality will be equal to 1. That is the absolute value. Okay. And now the question arises, why we need the normalized version? We can always do it with the degree of a node equal to the connections in the one hop. The need for normalization is very significant because since we have many centrality measures, also I will show you that there is a NetworkX library of Python in which a large number of centrality measures are there. So if we want to compare the centrality values of all the nodes in a network, then the scale is very much important to be uniform. So by normalizing a particular centrality, we are scaling the values down to 0 and 1. So when you'll have a uniform scaling for all the centrality values, then it will be easier for you to compare that which node is better in terms of what kind of centrality. So you'll see that for different centrality, this normalization factor will keep changing. Okay. Now, this was for the undirected graph. What if we have directed graphs? So the normalization factor remains the same, just that the numerator will change. So now we will be computing only those edges that are coming towards that node, so in degree. So all the in arrows. And for out degree, we'll be calculating all the out arrows. Now, we should move to the next centrality. And why? The reason is that degree centrality is missing a lot of information. So we cannot stay just on the degree part because it's not giving anything, any idea about the local neighborhood, its positioning in the relative neighborhood. So only it's taking into consideration the direct hop connectivity, but it's not taking the other neighborhood specific and especially outside the neighborhood, the information is severely missing. So now let's move to the closeness centrality. Now the closeness centrality keeps track of the relative distances from the node, one node to all other nodes in the network. So if we see the formula over here, in this case, the normalization is at the top. And in the denominator is the length of the shortest path between any two nodes I and j. So since the formula is such that it is inversely proportional to the length of the shortest path, which means that if a node is located, is located in such a distance that it is twice as far as other nodes, then it will be considered as half as central. Okay, so I will just quickly demonstrate that how this is being calculated. So it happens like this, since it is dependent upon the length of the shortest path. Okay, so for node number 3, if you can see that we want to first identify that which are the nodes that are in the first hop. So this is the first hop neighborhood set. This is the second hop neighborhood set. And likewise, we'll have the third and the fourth hop neighborhood set. We'll keep on doing this till we cover all the nodes in the network. And the computation is very simple. It is the number of hops we are taking multiplied by how many number of neighbors are there in that particular bucket. So it is 1 multiplied by 4, that's 4. So this way the computation is being done. In case of directed graphs, similar to the degree, we have in-closeness and out-closeness. So for in-closeness, the formula stays like this. Again, the normalization factor holds the same. And we'll see that in-closeness means that we'll consider all the incoming nodes. If the information content is in any of the node, then we will see that what are the different ways, the shortest ways through which we can reach node 1. So if we are at node 6, then there is a direct connectivity. If we are at 7, there is not a direct connectivity. Instead, from 7 to 9 to 2 and then to 1. So this way in closeness is computed, and just vice versa is the out closeness. So we'll go out from node 1. So if node 1 is having some information, then how node 1 will propagate the information to all other nodes following the shortest path. In closeness is also called the prestige. Next comes the decay centrality. So since the word decay is coming, so obviously we are going to see how the nodes are getting deteriorated, and there has to be a decay factor. Now this decay factor strictly it is between 0 and 1. So if the value of delta, that is the decay factor, is more towards 1, then it means that we are emphasizing the indirect connections. And if it is more towards 0, it means that we want to emphasize on the direct connections. So in this case, the formula will look like this. So it's the same, the length of the shortest path, but now it is raised to the power of the delta, that is the decay constant, so as to analyze how much the decay is happening. And the normalization factor in this case will be n minus 1 delta. You can always take up the star network, and you could see that in the best case, with this normalization factor, we'll get an absolute value of the decay centrality. The next is the betweenness centrality. So betweenness, here also the name suggests that we are looking for those nodes that are acting crucial to the network at the between of lying at the between of several communities. Okay, so you can take it as the crossing points or the bridge, the gateway that can keep the entire network connected. Okay. So mathematically speaking, it is the ratio of the number of shortest paths. So no more we are dealing with the length, but the number of shortest paths in which the node H is lying, that is for which we want to calculate the betweenness centrality. So if we are computing the centrality for node H, then our ratio will be the length, the number of the shortest paths having the node H in between somewhere divided by the total number of shortest path, including the ones in which the node H lies. And the normalization factor, you can see, is different. This is n minus 1 C2. Now, why it is n minus 1 C2? Because any number of nodes, we are taking the number of nodes 2 at a time from the pool of n minus 1 nodes. So we are leaving one node because we are taking it over here. So from the pool of n minus 1 nodes, every time we are taking 2 nodes. And hence this normalization factor is computed. So this is the normalization factor for betweenness centrality. And also from here, you can see that this is for the undirected graph. Okay. So if we have directed graph, then how this normalization factor will change? So this remains a question. You can do it sometime later after the lecture is over. Some examples which you can see that we can have a fair comparison over here that the nodes that is having a higher betweenness may not have higher degree and vice versa. Node number 3, you can see that the betweenness is very less, that is 0.1, but its degree is naturally more because it's connected to 4 nodes over here. But for node 15, the value in betweenness as well as in degree is quite high. In kind of star network, the star core is always having the highest value of betweenness. So that is always 1, because it's the only node that keeps rest of the nodes connected. If it's disconnected, then the network will get broken down into n components. And since we are following the shortest path, so if any two nodes in a star network gets connected, then that particular pair of node will not require any more traversal through this node H. That is the one for which we are finding out the betweenness. So that row will get 0, and similarly we get the centrality value depreciates. And one interesting fact is that the border nodes in betweenness have a value 0. So you can also see it over here. And for every time, you can also compute the normalization factor. And you can see that the border nodes are always having betweenness 0, because they need not to get traversed in any of the pair of nodes in which the information has to flow. Now, one more interesting thing is whenever a network is given to you, as you have seen, the formula of betweenness centrality, the complexity is quite high. Now, to reduce the complexity, there are different approaches that have been carried out, and betweenness is considered a really very important centrality metric, especially in the transportation networks and many more friendship networks and product recommendation networks, etc. So straight